hopefully you all agree that SQL is awesome. One of its great powers is you tell the database the result you want, and it figures out the fastest way to execute it. But this leaves you a problem. If the database is figuring out how to execute your query, if it's running too slowly, how the heck do you go about making it faster, right? It's a bit of a puzzle, or it can be a bit of a black box. So if you start asking around people, well, how do I tune SQL queries? One of the first things, or a common thing they will tell you, is to look at the execution plan. Now, when you're just starting out, you probably looked at some of these plans and just like, I don't know what the heck that means, right? I've looked at this and it's just gibberish to me, essentially. How does this help me understand performance and what can I do about it? Well, the thing to remember is that the execution plan is like the optimizer's driving directions. So if you go on a route somewhere, it'll say turn left at this junction, turn right, go this far, so on and so forth. An execution does something like that for the database. So for example, let's imagine we're living in the world where we have real physical conferences, and I'm traveling over to Azerbaijan to actually be with you all in person. So in order to get there, my route might look something like this. I'd get the train to London, get on a plane, fly to Baku, and from there, travel on to wherever the event actually is. So we draw these arrows on the map, and it's pretty clear roughly where I'm going, at least. We'll see if you give someone directions and say, here's a map, here's the arrows, follow them, most people will be able to do it. Fairly straightforward. But when we've got a plan like this, you're just like, well, hang on, that's just some text there. Those don't look like directions to me. How the heck do I understand those? So that's what we're going to do in this session. We're going to look at how essentially we can draw the arrows on those execution plans so you can see the route the database takes through the plan, and then look at some things you should look for to help you optimize the query, things that you could do, actions you could take to make it run faster. So, hi everyone, I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team. It's my job to help get the best out of the Oracle database and hopefully have a little bit of fun whilst doing so. And as I said, with that in mind, today we're going to be looking at execution plans and SQL performance. So what we want to do is draw the arrows on this plan. So the first thing to note here is the execution plan is a tree, not a physical tree, but a data tree. That means each operation has at most one parent and can have many children. So if we look at our plan here and go for this hash join, its parent is the first operation above it that is indented to the left. So that's that select statement there. Its children are those that are below it that are indented to the right. So that's those two full table scans. So the parent-child relationship is determined by its position up and down, but it's also how far indented it is. Quite often when getting plans or by email or on the internet, people will lose this indentation. So everything's just fully lined up there on the left. Makes it really, really tricky to spot this parent-child relationship. I mean, I might be able to do it in a fairly simple two-table plan like this, but if you've got 20, 30, 40 lines in your plan, it gets very tricky very quickly to figure out how the relationship goes together. Please, if you're sharing execution plans with people, make sure you use a fixed width font, such as Courier, and preserve the indentation. Otherwise, it gets very, very tricky to figure out what's going on. So we've got our parent-child relationship, and our tree looks something like this. So how do we actually traverse the way through this tree? Well, we start at the root and then travel down. And what we're going to do is go down the plan to the first unvisited leaf. We'll read the rows out of that. It will pass those rows up to its parent. And then once we do that, we will repeat the process. Look for the next unvisited leaf below that plan, that operation, go back up once we've got it, and so on and so forth. This is a depth-first search of the tree, okay? So if you've drawn it out in the tree structure like that, you can use depth-first search to follow it. Let's look at how we might draw the arrows onto a plan like this. So we'll start at the top, our root, select statement, and what we'll do is we'll travel down to the first unvisited leaf. So that's the operation with nothing below it that is indented to the right. So that's this full scan of the colors table. We'll read the rows out of that, pass them up to the hash join, its parent, And once we've gone there, we'll look for the next unvisited leaf. Well, that's the full scan of the bricks table. Read those rows, pass them up to its parent. At this point, we've read all the tables in the plan, so all that's left is to pass the rows up to its select, and we're done. So pretty straightforward, nice and easy to break us in. Let's level it up a little bit. Let's go for a 4-table join. Okay, so again, we'll start at the top, that select statement, and we will travel down the plan till we find the first unvisited leaf, the thing with no children below it. So that's that full scan of the colors table. We'll read the rows out of that. It will pass them up to the hash join. We then look for the next unvisited leaf. That's the full scan of the toys table below it. Read the rows from that, pass those up to the hash join, and then we look for the next unvisited leaf. Well, we've read all the children of this hash join, so we skip that step and go back up to the next hash join. From there, we'll look for the next unvisited leaf, and that's a full scan of the pens table, and keep going through the plan following this kind of snaking pattern a little bit like this. So 4-table join. Let's level it up again, and this time we will use the same 4 tables but get a very, very different looking plan. We've got something like this. Looks a bit more complicated, but the process for following it is exactly the same. So what we do is we start with a select operation, go for our full table scan of the colors table, pass them up to its parent, that's the hash join, and from there we then look for the next unvisited leaf. So at this point we need to go all the way down here to the bricks table. So that's the next operation which has no children. And we will then work our way through these rows, which are the children of this union all. Now, usually this will happen serially, one after the other. So we'll read bricks, toys, and pens. If you're running this in parallel, the database could actually read all 3 tables at the same time. But just a standard serial plan, it'll read them one after the other, and then it'll pass the rows up to the union all, which will merge them into a single result set. At this point, we've read all the data from all the leaves, so all that's left is to pass the rows back up through the plan, through all the operations, the joins and the group bys, and so on and so forth. So, seemed a bit more complicated, but the process is exactly, again, the same. So, let's level it up again, and we'll go for a plan that looks like this. Now, first glance, you might look at this and say, hang on a second, well, actually, we're back down to just 2 tables. It's easier, right? Why is this any different, or what's harder about it? Well, look closely at the plan, and you will notice something missing. There's no join operation in this plan. So what's going on? How do we get a plan without a join in it? What kind of query would generate this? Well, what we have is a scalar subquery, a query within the select statement of the other query. Now, the thing to note here is the database processes SQL statements starting with the from clause. So the first thing it's going to do is read the rows out of the colors table, check those that pass the where clause, there isn't one here, and then it will process the select clause. So we're taking the rows out of the colors table, and for each one of those that come out, we are going to run this subquery, okay? Now, if we look at this plan here, you'll notice that colors is actually right down at the bottom. So it kind of breaks that access to first unvisited leaf first, or the topmost leaf is the first one you should read. So you might go, how do I know I'm supposed to do this? Well, a couple of clues. First up, you'll have a scalar subquery in your query, so you'll notice it, select within the select clause. But secondly, we haven't actually joined the bricks table. There's no join operation in here. It tells us there's something a bit different going on. So one of the reasons I highlight this is partly because it breaks the rules, but also to point out there are edge cases and things that break the rules or bend them slightly in all sorts of weird and wonderful ways. There's edge cases all over the place when it comes to reading the execution plan. So I say these are rules, mostly they're guidelines, principles you should follow. Ultimately, to really understand, also useful to understand how the database executes SQL, which order it processes things, and so on. Anyway, how do we read this plan? Well, we have to read the rows out of the from clause first. So we'll read them out of the colors table. Then for each of the rows we get here, we can then run the scalar subquery. So what we're going to do is run that, read through the full table scan of bricks table. And we could end up doing this many, many times. Worst case, we actually do it once for each row we get from the colors table. A lot of full table scans, right? Now, there are optimizations in Oracle database, which mean it's probably not going to be that bad, but it could be quite slow. We could end up full scanning that bricks table many, many times. So just take a quick break at this point, and then there's a question from Sunil. Is there any query script to display the plan from the first leaf child where the plan is accessed first? I mean, there's scripts you can use to get the plan. If you're asking if there a script which shows you which order it reads the operations, I don't know one specifically. If that's your question, Sunil. If you mean something different, you'll have to clarify exactly which order it reads. Yeah, I'm not aware of one specifically. Yeah, you'll have. This is where you need to kind of understand what's going on and figure out what's actually happening. So sorry about that, but if anyone else knows, please share and let us know. Okay, so we've seen the directions. We know the route we're following through the plan. The next question is, of course, well, how do we make it faster, right? Just knowing the route in of itself isn't really enough to help you make your query faster. If we go back to our real world traveling example, if I'm traveling from my house here in the UK over to Baku and somewhere in Azerbaijan, then this is going to take me a while. And if I'm coming to you and going, well, this journey took me a really long time. Can you help me? Can you help me get there faster? Your answer is probably like, well, I don't know how to do that. I don't know which route you take, how long it took you, that kind of thing. In order to answer that question and figure out, is there a faster route we can take, there's various questions you'll want to ask and get the answer for. Things like, well, how far is it? You know, it's quite far, about 4,000 kilometers. How long was it estimated to take me? How long did it actually take me? You know, if it was estimated to take me about 13 hours and the total journey time was like 24 hours, it's a sign that maybe there's a faster route available, at least on that particular day, right? So how close was the estimates you get from whatever your favorite travel application is versus how long it actually took? And of course, most importantly, what other routes are available? You know, as far as I know, there aren't actually that many direct flights from London to Baku, if any at all. Certainly not at the moment. So if I've gone in directly, are there all sorts of other routes I could have taken to get there? So you need to answer these kind of questions to figure out what other routes are available and how we could get there faster. It's kind of the same when it comes to tuning SQL statements. We've got our plan, and it's like the plan on itself doesn't really tell you how to make it faster. We know the route, but we need the details, how long it took, how far it was, that kind of thing. And there's 4 key questions that you really want to ask. The first step is the row estimates. So the row estimates, how many rows the optimizer thinks it's going to get from each table, is one of the key decisions, because it determines which order it's going to access the tables and which join types it's going to use. So generally speaking, so you want those to be pretty accurate. Generally speaking, if the row estimates are reasonably accurate, so within an order of magnitude of number of rows the database actually gets, then generally you've probably got a good plan. Or to put it a slightly different way, if the number of rows the optimizer is estimating is wildly different to the number of rows you actually get, so an order of magnitude or more different, there's probably a better plan available, or it's worth checking to see if there's a better plan available. So are those row estimates accurate? If they are, well, the next question we can ask is, well, how much work did we actually do? How much effort did the database go to fetch and process them? And in this case, the key thing you want to look at here is I/O. So there's 2 key resources when processing things on computers, CPU and disk. And when it comes to SQL performance, disk dominates. So you want to, all other things being equal, you want the plan that does the least I/O, does the least work. And the metric you'll often hear talked about here is consistent gets. How many logical I/O operations did we do? We've got 2 plans, and one of them has fewer logical I/Os, fewer consistent gets. All things being equal, it will be the faster plan. So how much work did we do? Having identified that and seeing how much work we've done, next question is, well, can we find a way to do less work? Can we read those rows with less effort? And this is where we're talking about creating data structures. Things like, are there any indexes we can create? Can we create materialized views? Maybe we need to rewrite the query slightly, that kind of thing. What can we do to reduce the amount of work we do? So 3 key questions there. And of course, finally, and perhaps the most important one, how long did it actually take? And how long did each individual operation in the plan take? After all, customers don't really care about the answer to these first 3 questions. They care about how long it takes. You know, if you go to them and say, you know, we dropped the consistent gets from 1,000 down to 50, they'll probably be like, what? Where if you say, you know, we got that query, it's gone from 10 seconds down to half a second, they'll be like, okay, yeah, I know what that means. That's really useful. And the thing to note here is how long it takes is kind of a consequence of these first 3 things. Just like if you want to complete a journey faster, so you're driving somewhere and it takes you an hour, you want to get there quicker in less time, well, how do you do that? You don't do taking less time. You either drive faster or you take a shorter route or a quicker route. So similarly, when it comes to reducing the time it takes, you want to tweak these first 3 things, and then hopefully it'll end up reducing the runtime. Now, it's possible that the first 3 answers could be wrong or bad. The row estimates could be way out, but the query executes in 1/10 of a second, you know, well under a second. Chances are that's good enough, and you don't need to worry. If things are fast enough, then you can move on with your life and do something more important. So how long did it take is ultimately king. So how do we get this information? Well, there's lots of tools you can use to get an execution plan. One of my favorite is DBMS Xplan. So you can use this to get plans in text format, which you can then easily share with people on QA forums such as Ask Tom, send by email, that kind of thing. So a few key things you want to do when getting a plan using this. First up, make sure you include this gather plan statistics hint. Without that, or you can set statistics level to all in the session, without that information, we will not capture things like how many rows we actually processed, how much work the query actually did. So you really need to do that. And then use a format to display that information. There's a whole bunch of them available, but if you just use all stats, that will show you every possible thing, every metric that the database has captured about that plan. So it's reasonable or easy enough to start with that. You can use different formats if you need to be a bit more targeted. Okay, so we've got our plan. We've stuck our gather plan statistics hint into the query, run it, use DBMS Xplan to get it. You'll then see some extra columns on the end of the plan, on the right of the plan. And that are these starts, E rows, A rows, A time, and buffers. You might see some other ones as well, but these are 5 key ones that you'll always see. So starts, pretty straightforward. How many times did we do this thing? E rows, estimated rows. How many rows did the optimizer think it would get for this operation in the plan? And how does this compare to the A rows, the actual rows? Like I say, you want to check that these are broadly similar figures. Then we come on to the A time, actual time. How long did this operation take? And the buffers. So I was talking about consistent gets, logical IOs. That's what this is showing you. How much logical IO work did this query do? And again, we want this figure to be nice and low, generally speaking. Another thing to note here. So these first 3 columns on the right here are step specific. So that means it's saying this individual operation started this many times, the optimizer estimated this many rows, and it got this many rows. The A time and buffers columns, on the other hand, are cumulative, right? So to figure out the time and IO for a particular operation, you need to subtract off the figures for its direct children, okay? So we're not looking, when we're looking at the totals here, we're looking at that top line. So this query took about 1/100th of a second to execute and 24 buffers in total. We don't sum those up to say it took about 1/10 of a second in total and used about 100 buffers. No, the top line is the overall total. To get the individual totals for each operation, you need to subtract the figures off for its direct children. Okay, so that's the kind of things we want to look at in the plan. Let's look at now some examples of common things you want to look for where the database has got it wrong, or there's things we can do to help the optimizer find a better plan. And I'll start off with that first one, the row estimates. So incorrect row estimates is a very big cause of the optimizer choosing the wrong or a slower plan. So let's go back to a 4-table join like this. And if you look at it carefully, some of you might notice something interesting going on here. That's that merge join Cartesian operation. So this can be a sign that you are missing a join in your query. So if you see that, just double check you've got all your joins written correctly. But the optimizer can still choose this, even if you've got all your joins, if it thinks it's going to get exactly one row from the first table in the join and link it to every other row in its other child. So if we look over here on our bricks table, the optimizer is estimating it's going to get one row from the bricks table. And provided we are getting just one row from the bricks table, then a merge join Cartesian of one row to any other data set is quite often the fastest way to do it. So how many rows are we actually getting here? 24. Okay, so we're an order of magnitude out here, and the side effect of that is we end up doing this buffer sort operation below it 24 times. So notice the starts for the next child matches the actual rows for the previous child. We're doing buffer sort 24 times for the 24 rows we got from the bricks table. So merge join Cartesians get very slow very quickly if we're not getting just one row from the table. So we're way out with our row estimate there. Now let's look at the estimates for the buffer sort itself. We're estimating 5 rows, but getting 120. Again, we're out by an order of magnitude. In fact, we're out by a factor of 24. 5 times 24 is 120. Oh, that's interesting, right? 24 starts times 5 estimates equals 120 actual rows. So a slight tweak to that formula. You're not just checking is E rows equal to A rows, are they roughly the same? You're checking is starts multiplied by E rows roughly equal to A rows. If they're in the same ballpark, then you're good. So in this case, our buffer sort is actually estimated correctly. I bang on, even though at first glance it looks like it's quite far out. Finally, we can see we've got another misestimate here. We're estimating 100 rows from the colors table, but getting just 3. So again, we're out by an order of magnitude or more in this case. So we've got a couple of tables with incorrect row estimates. So we've got wrong row estimates in this table. What do we do about this? How do we go about improving them? Right? Well, gather statistics. Okay, we gather statistics on the table, and the optimizer now has the correct or pretty good row estimates for all the operations in the plan. Now note, it's pretty rare you actually need to gather stats manually yourself these days. Usually the optimizer will take care of it. There's a background job in Oracle database, which when the rows have changed more than 10% by default, it will gather stats for you. So it's relatively rare you need to do this. But if you're doing a big batch processing, let's say you've just updated, deleted, inserted more than 10% of the rows in the table, you might want to do it manually. Or if you've got like a staging process, you truncate the table and then reinsert a whole bunch of rows, again, you might want to do it manually. But generally speaking, you can rely on the database to just handle all this for you. So let's look at, see the estimates there on. Let's look at some more examples of incorrect row estimates where the optimizer doesn't help you automatically by default. So I've got 2 queries here. One where I'm searching for the red cylinders and one where I'm searching for red prisms. And in both cases, the optimizer estimates just 3 rows. But how many rows does it actually get? Well, we get 8 red cylinders and 0 red prisms. Okay, so 8 and 0. So neither of these estimates is correct. So why is this? What's going on? Well, there's a relationship between the columns. All the red bricks are cylinders. We don't have red bricks of any other shape. And the optimizer doesn't know this by default. It assumes that they're independent and says, well, about a third of the rows are red, about a third of the rows are cylinders, so I'll multiply a third to a third and expect about a ninth of the rows. And in fact, all the red rows are cylinders. So we need to tell the database about this relationship. And we can do this with the method opt. So we can gather stats on an expression, so color and shape as a pair. Check those as a combination, as a combined thing, and say, what are the unique combinations here? Do this, and it can identify that all the red bricks are in fact cylinders, and we can get much better row estimates. Bang on, in fact, for our red cylinders. Now, I said there were no red prisms, so why isn't it estimated 0 rows? Well, estimating 0 is a very, very dangerous thing. Why? Well, these estimates will then percolate up through the plan, and we can end up with multiplying by 0 further up. 0 times anything is always 0, or dividing by 0. Either way, we can end up with problems. So the optimizer will, at its lower bound, estimate 1. It's gone for 3 here. There's various reasons for that. Don't really have time to go into, but key thing is we've got the correct row estimate for our red cylinders. Let's move on to another case where it gets it horribly wrong. So all the colors in this table are in lowercase. So upper of the color column is going to be equal to uppercase red, right? We can see this is going to return us all the rows that have the text lowercase red, right? You should expect the same row estimate. The optimizer, on the other hand, just doesn't know that, and it estimates just one row. And the problem is, again, this function is a black box. It doesn't know the result of running upper on that column. It has to actually do it to get some statistical information about it. So in order to capture that, what we need to do is put upper, calculate statistics on the expression upper of color. Do that, and now we're back onto bang on row estimates. Okay, I see there's a few questions come in, and Loy, how should we gather statistics for tables, and should we do it for all tables or only important ones? So like I say, by default, the database will gather statistics for you in all modern releases of Oracle Database, unless someone's switched off for some reason. So generally speaking, you don't need to fiddle with this. And you should gather stats on all tables because, even tiny tables or even unimportant tables, you can end up joining in, and if the stats are way out, then you can end up with horrible execution plans for those. So most of the time, you don't need to worry about this. But if you've just done big batch operations, you might want to do it manually. Also, if you've got really, really huge tables, like say tens of millions, hundreds of millions, billions of rows in the table, the optimizer by default will only gather stats when 10% or more of the rows have changed. You might want to change that to happen a little bit more frequently. So you can do that with by setting some table preferences that will tell the optimizer gather stats a bit more frequently. If we've got some time at the end, I might address those. Okay. All right then, so let's move on. I see there's some other questions, but they kind of relate to some stuff I'm going to talk about in a minute. So let's move on to the next problem, inefficient access. So let's go back to our two-table join, full scan of both the tables. And here we're getting just one row from both of the tables. But how much work are we doing to get them? Well, we're doing 7 or 6 logical IO operations to get just one row, right? And the relationship's kind of the wrong way round here. We want to do one IO operation and get lots and lots of rows, not do lots and lots of IOs to get just one row, okay? So in this case, it doesn't matter what the row estimates are, or, if the row estimates, let's assume they are bang on, we're estimating one row, we're getting one row, but we're doing lots of work to get that. So how do we resolve this? What can we do here? We want to find these rows more efficiently. Oh, this is where we want to create some indexes, right? We can help the optimizer find those rows very, very easily. So in this case, now we've done that, we're going to get one row from each of those tables. We can use the index, look up the index to find the entry for that row, and then go to that table for that specific row. So in this case, we're just doing 2 IOs for each table, one to read the index, one to read the table, giving 4 in total for our 2 tables. So this drastically reduces the work. So I see Mia asking, how can we know for which column we need to create an index? This is one of the things you want to look for. Are you doing a lot of IO to just fetch a small number of rows? Okay, it's a bit more complicated than that, but broadly speaking, if you're fetching a few rows, a handful, and doing a lot of work to get them, sign that probably you're missing an index. So that's one of the things you want to look for there on that, Mia. Okay. Babu, upper will make it as a function-based index. So the query we had upper color to look for the uppercase red. If we create a function-based index on that, then the database can use the function-based index to find that row. So that will be more efficient than a full table scan, assuming we're finding few rows, of course. But that won't necessarily help us with the row estimates. The optimizer still doesn't necessarily know that doing upper of this column actually just returns few rows. So function-based index will help find rows faster, but it may not help with our row estimates as much as you would hope it would. Okay. All right, so let's move on to the next thing. I see there's more questions. Need to keep moving. Hopefully I'll have some time left at the end to address some of those. All right then, so next potential problem we're going to look for, repeating work. So let's return to our scalar subquery plan. So we've got our sort aggregate. So show why, just reinforce why this can be so bad for performance. We're starting this full table scan of the bricks table 3 times. So we read all the rows in that table 3 times. Okay, doesn't sound right, does it? We are doing a lot of extra work here. Ideally, we want to scan it just once. So how do we fix it in this case? Well, in this scenario, the fix is a little bit different. We can't just rely on the optimizer to find a better way to do it. After all, if it was able to transform the query some way, it would have already done that. You know, the optimizer is actually pretty smart. And in some cases, it can take a scalar subquery and turn it into a join. In this case, it hasn't. So we need to do that manually and turn this query into a join. So now we've no longer got a select buried in the select of our statement. So it's, you know, generally, if you've got a scalar subquery, a select within the select, you probably want to, there's probably a faster, more efficient way to do it. Either turn it into a join, sometimes you want to use analytic functions and so on and so forth. Not a hard and fast rule. There are still some cases where scalar subquery can be better, but generally speaking, you want to look and think, how can we reduce the work we're doing here? We go back to our new plan, or go to our new plan, I should say. We can see that we are now reading each table just once. So exactly what we wanted, significantly reducing the amount of work we're doing. All right, next possible problem, reading many rows and returning few. So here we've got a query, we're full scanning the bricks table and getting 100,000 rows from it. But in our results, we're just getting 3 rows in the output. Why? Well, we're kind of doing something like this. We're doing group by color and counting the rows. Now there's only 3 colors in the table. That means at maximum, we're going to get 3 rows in the results. But as the input, we're going to get the entire table. This could be hundreds of thousands, millions, billions, whoever, who knows. It could be a really, really massive table. So we're doing a lot of work to get a few rows in the output. So rather than scan the table, it'd be better if we kind of pre-compute this result and save that in a table somewhere. You know, after all, scanning 3 rows is always going to be super, super fast. Scanning a table with just 3 rows in it is going to take basically no time whatsoever. So now you could go and kind of roll your own and write some process to save these in a table and keep them in sync when the data changes, or you create a materialized view, okay? So if we create a materialized view, the database stores the result of this query in a table in the database. And if we've got query rewrite enabled for it, like I have here, then the database is able to go, oh, I see you're executing this query group by color. I've got this materialized view where we've saved the results for that query already. Well, instead of running the query against the table, I could just look at the results of the materialized view here, right? Save ourselves a whole bunch of work. So we can do that with a materialized view rewrite access full. And now we're just scanning 3 rows in total, much, much faster. Now, there is a lot more to materialized views. You need to make sure the database keeps them in sync. Ideally, you want them to be fast, refresh, on commit. There's a whole bunch of stuff I could talk about when it comes to doing that. But the key thing to remember here, if you've got queries which aggregate a large sum of data or a large volume of rows and return just a few, look at materialized views. Very, very common example where you would do this. Give me totals per day. What is the total number and value of orders per day for the past week, past month, even the past year? If we're getting daily totals, we're going to get at most 366 rows in the results, right? But as input, like I say, you could have hundreds of thousands, millions, billions of rows as input. So using a materialized views, we can say, we're only going to have to scan at most 365, 366 rows here, saving ourselves potentially a lot of work. So lots more ins and outs of those. I've got some links at the end to kind of help you follow these and see what how they work in a bit more detail. All right, final problem I want to cover here, and I see there's a lot of questions, so I'll have time to cover those in a minute. So, final thing, unrealistic requirements. So these are, so far we've talked about things you can do to help the query run faster, but it's always worth remembering that if you're doing a lot of work, ultimately it's gonna take some time. Every now and again, you get someone who asks a question like this. I've got a query, it's reading 10 billion rows, and it's taking me 10 seconds to get the results. Can we get it in like a millisecond or a microsecond or something daft? And at this point, you're just like, kill me now, right? You know, there's no way we can read that number of rows and return them to the client that quickly. So ultimately, if you're processing huge volumes of data, it's going to take a while, right? If we go back to query returning 10 billion rows, first question I ask is, well, what are you doing with that data? There is no person who is sitting there and paging through 10 billion rows of results, right? So client application doesn't need this. Why are you doing this? Only genuine examples I could think of are things like exports, where you're transferring data to another system. And again, they tend to be back-end processes where it tends not to matter too much if it takes too long. So the thing to remember is if you're processing large volumes of data and particularly returning them to the client, why are you returning them to the client? What is somebody doing with them? Do we really need to process all that data? If no, well, let's not do this query, right? Save ourselves 10 seconds completely, remove the limit, bring the work right down to 0. So fundamentally, processing large volumes of data will take some time. All right then, quick recap on getting better plans. So first thing you want to look is check the row estimates. So you want to check, like I say, is the number of times the operation started multiplied the estimated number of rows for it roughly equal to the actual number of rows. If these are wildly different for lots of steps in the plan, good sign that by tweaking the stats, then you can get better plans and a more efficient access. This is one of the key ways the optimizer decides not only how to join the tables, do I use a hash join, nested loop, that kind of thing, but which table to start with first. The optimizer prefers to start with the table that returns the fewest rows, okay? So even stats on small tables can have a big impact here because it's looking for the table it expects the fewest rows from first, and it will start the whole plan with that. So check the row estimates. Assuming they are reasonably accurate, you can then start looking at things like creating faster access paths. Do we need to create indexes? Should we partition the table? Do we want to create materialized view? Should we use in-memory? That kind of thing. How can we read the data we need to faster or reduce the work we need to do to read that data? And finally, of course, once you've done these first two things, quite often you'll be in a situation where the data query genuinely does process lots of data, and you just have to kind of accept that things take some time. Review your requirements. Do we really need to read all that data? Can we run a different query? Can we run it in a different way? Can we offline the process, run it in the background, rather than while the customer's actually sat there at their application waiting for it? That kind of thing. If you've done all you can with these first two, then it's time to start thinking, well, why are we actually doing this? Actually, it's always a good place to start and say, why are we doing this at all? Do we need to do it? Can we do something completely different? That's actually always a good place to start, because often you'll find that we don't need this query anyway. Okay, so where do I go from here? So if you want to learn more about reading a plan, I've got a blog post which kind of walks through that process, showing you how to draw those driving directions onto the plan. You can get the scripts that I've used to create the execution plans and the queries in this presentation. So I've got live SQL tutorial script showing you that. And I've got my free performance course, Databases for Developers Performance, which gives you an introduction to SQL performance. I'll recap all of the things I've talked about today, how to read a plan, also go into more detail, things like how to create indexes, when indexes are useful, how to create materialized views, some ins and outs of those. So if you want to get more of a start on SQL performance tuning, check out that course. It's free. It's available for you to take anytime you want. Okay, we got a minute or two, and I can see there are quite a few questions, so I'll take a few of these very quickly. So let's see what I've got. So Mia, also in simple terms, what is access path and predicate information? So the predicate information will appear at the bottom of the plan, and it will tell you how it shows you how it filtered the data, which restrictions it applied to which columns, or which conditions to which columns at which operation in the plan. And there's two types here, access and filter. So access means all the rows returned by that operation, or only reads rows that operation returns. So this is usually when you use an index. Look up by primary key, find the primary key, we've accessed the one row, return it to the previous one. Alternatively, it could be a filter. That means we're going to read more rows than this operation returns and filter them out in the process. So you usually see this with a full table scan. Full scan, we're going to read all the rows, but we're going to search for those where the color is red. So we read all the rows and filter out all those rows where the color is not red, okay? So filter, read more data than we're returning. Access, only read the rows we're going to return. Generally, access is faster, but it's a little bit more to it than that. Fernando, how system statistics like Exadata specific statistics change the plan? There is some ins and outs in there. For Exadata, you will want to look at system statistics. In general, it's the row stats that have the biggest impact there. So generally, you want to focus on the row stats rather than system statistics. Anonymous, how about Q tables and EBS? I know nothing about EBS, sorry. So not much I can do to help you there. And AJ, how joins should be made? We have driver table concept in SQL. Can you tell us more on this and how to decide which one should be driver table? So AJ, the thing to remember here is the optimizer makes this decision, and it chooses, or it tries to choose, the table that returns the fewest rows. And this is something you don't pick that, it's up to the optimizer. And like I say, it tries to choose the table that returns the fewest rows. So let's imagine we got our 10 billion row table. We're doing a primary key lookup of it, so we get just one row from it. That could still be the first row we read because we're returning just one row and we're using an index to find it. So that's why looking at those table statistics and how many rows we're actually going to get is key for that. Okay, let's see. Keywell, so how does this clustering factor affect performance? So clustering factor has a big impact on performance. So it's a measure of how closely the physical order rows are stored in the data matches the logical order they are in the index. So the index always sorts entries according to the column values. Rows in the table, however, could be placed anywhere on disk. there's a lot more I could say to talk about that. It's a very important concept. If you want to know more, take my course and I'll go into a lot more detail on that and follow up on some of these links that will show you some of these other things. Yigal, what is the limit in using aggregated MV on frequently changing column data on large data sets? So thing to remember there, Yigal, as I said, for materialized views to be most effective, they need to be fast refresh on commit. So every time you change data in the tables in materialized view, the database will also update materialized view. If you have got a very, very write heavy application, it might add too much overhead to your processing. Ultimately, it's something you've got to measure for yourself. There's various other techniques you can use to look around it. Like I say, don't have time to go into that a bit more detail. We're slightly over time. Mirela, have we got time for one or more two questions?
Yes, we have time for 1 or 2 questions. We can stay another around 3 minutes. We are okay.
All right, I'll take a couple more and then
yes.
I think.
Yes.
All right,
please.
thanks.
Yeah.
Okay. Okay, so anonymous, how about where most of the time spent in execution plan, please? Okay, so that's, like I say, you want to look at that A time, actual time column. And to find the time for an individual operation, you need to subtract off the values for its 2 direct children. This is probably one of the trickier ones to spot, particularly with using DBMS XPlan. You notice it's only granular to hundredths of a second, which often is not granular enough. I mean, if an operation takes 4 minutes on its own, got full table scan, takes 4 minutes, it's pretty easy to spot. But, if you've got a fast-ish query, say a couple of seconds, but you need to take it down to sub-second, you really need that more granular information. If you look in the SQL Monitor report or AutoTrace in SQL Developer, gives you precision right down to microseconds, much easier to spot there. And it's a graphical plan you can expand and collapse and do all sorts of cool things with. So it's much easier to spot using AutoTrace in SQL Developer. I'd check that out if you're struggling to spot the slowest parts there. Anonymous, what is the rainbow behind me? So that's something my kids made for me a little while ago. So there you go, there's the rainbow. Just a bit of fun. Hope you appreciate like that. All right, one last question. Uday, how to get E rows and A rows when we can't use gather plan statistics hint while running the query? Okay. What you can do is there's a parameter, statistics level. You can do an alter session, set statistics level to all, and that will capture this information for every other query or every statement in that session. So let's say you've got some code you can't change for whatever reason. You can alter statistics level to all, run the code, and get the execution plans afterwards. So that's how you do it if you're not able to change the query itself. And I think just one last question from Anonymous. Are there any significant performance issues using old implicit syntax for joins? So if you're looking about, doing your joins in your where clause, comma separated list tables versus ANSI join on, no, there's no performance difference, or there shouldn't be any performance difference. In fact, you may find in some cases that using the old style works out better. Why? Well, the Oracle optimizer rewrites the ANSI style joins into the old style joins internally. So, 99.9% of the time they come out exactly the same. Every now and again, there are still some edge cases and quirks where the old style is better and comes out faster, but most of the time you don't need to worry about it. Alrighty then, so I think it's me to wrap up now, Mirela. I just want to say I really hope you enjoyed this. More importantly, I hope you all learned something. Stay safe, and I hope we can actually see each other in person again sometime soon. Goodbye.